Okay, so our next speaker is Benjamin Giblin with slicing through the tension, the future of quick gravitational lensing.
Thanks very much. Yes, I'm Benjamin Giblin. I'm a Stephen Hawking Fellow at the University of Edinburgh. So as you can see, this talk is all about slicing through cosmological tensions and what I see as the future of weak gravitational lensing cosmology. So as this picture is supposed to imply, this is all about taking the path less traveled in these types of analyses in order to improve our cosmological constraining power. So this work was done in collaboration with Yanchuan Chai and Zheshan Darap at various universities. And you can find some interesting reading on what I'm about to say at this archive link. So without further ado, this is what's coming up. I'll first summarize how cosmological weak lensing, also known as cosmic shear, actually works. I'll then say a bit about how we can do better and improve our cosmological constraining power. I'll then show some cosmological constraints from a new statistic called the lensing PDF that we can improve our constraining power with, and contrast that with the constraints you get from more conventional lensing statistics, and then show a look to the future. Okay, so this is a quick summary of how weak lensing, also known as cosmic shear, actually works. So essentially we have observations of millions, or in the future billions, of galaxies out to redshifts of about 1, 1.5, that kind of range. And the light from these galaxies passes through regions in the universe of space-time curvature, and that curvature is caused by the large-scale structure of the universe. So this is a massively exaggerated picture of what this looks like, but this deflects the path of the light from these galaxies, and that causes very small distortions to manifest in the shapes of those galaxies and changes their orientations by a very small amount. So this is why we call it weak lensing, and those distortions that manifest from lensing are called shear. So this is why we call this cosmic shear. And the way we tend to extract the cosmological information in these observations is by measuring the shapes and the orientations of these galaxies as a function of their angular separation on the sky and as a function of their redshift. So this produces a statistic which we call the shear correlation function. So how correlated is the shear of these galaxies? And that produces constraints that look a bit like this. So these are some of the latest cosmic shear constraints from the most recent data release from the Kilo Degree Survey. This analysis was headed by Marika Asghari in the audience here. So on the x-axis, you have the matter energy density. On the y-axis, you have the amplitude of density fluctuations, sigma 8. And from lensing, we get these 3 banana-shaped contours. These are all from lensing, and they're just different 2-point statistics that quantify that weak lensing information. And we have this banana-shaped degeneracy, because in lensing, we can't tell the difference between a universe that has very high omega m, so a lot of matter that doesn't cluster very strongly, or the inverse of that, where a universe that contains less matter, but it clusters quite strongly. And what I want to highlight here is this lack of overlap, of course, with the constraints from the Planck analysis of the CMB. So this is, of course, cosmological tension, of which I'm sure many of you are aware. And this lack of overlap could be indicative of physics in the universe that we don't understand, unaccounted for systematics. It could just be a statistical fluke, and in fact everything is hunky-dory, shall we say. But I think one of the only ways that we'll infer deeper insights on this problem without having to wait for data from Euclid or LSST is to gain more information from our data and improve the constraining power of lensing with the data we have available now. And that is possible to do because we know that these 2-point statistics that generate these contours, they don't extract all the information that is present in the data. That's because two-point statistics extract information up to second order. And that means if the density distribution in the universe was Gaussian, two-point statistics would be optimal because the Gaussian is fully summarized up to second order. But the density distribution in our universe is not Gaussian, especially on small scales, very dense regions. And so there is information that is beyond the reach of these statistics that generated these contours. And that's what we hope to extract with new statistics. So one of the ways I propose to extract some of this information is by reconstructing the projected matter density from weak gravitational lensing. And this is possible because where the shear of our galaxies is stronger, we know that there was a greater abundance of matter along that eye line. And so we can reconstruct sort of where the projected density was higher and lower. And so I'm showing 3 projected density maps here. For those in the field, they'll refer to these as convergence maps, but they're projected density maps. And these are 3 maps from the exact same simulation. The only difference here is the amount of smoothing that has been applied. And that's a choice you are free to make in this analysis. And depending on how much smoothing you apply to the maps, you'll extract structures of different physical scales. So a low amount of smoothing corresponds to highlighting small scale features in that large scale structure, and high amount of smoothing highlights the inverse of that. And I'm showing these because I will demonstrate that these maps contain different cosmological information that is complementary. And in fact, we should use all 3 of these when constraining cosmological parameters. So how do we summarize the cosmological information in these maps? We use a statistic called the lensing PDF. So this was discussed by Daniela earlier. So here on the x-axis is the density, and on the y-axis is just the probability density function of these projected maps. So it's a very simple and very powerful statistic. You're just taking the histogram of these different maps, and they generate PDFs where, for example, if you apply a lot of smoothing, you suppress small scale features where you might have more highly dense or highly underdense features in the map. So I am proposing we use all of these statistics in our likelihood when we constrain cosmological parameters. So let's look at the cosmological sensitivity of this statistic. So these PDFs look very Gaussian, and that's because they are measured from Gaussian simulations. And you can see the dependence on the matter energy density and the amplitude of density fluctuation sigma 8 in the upper and lower panels. So as you increase these parameters, you get a universe that has higher abundances of very overdense or very underdense regions. Okay, so when we started this analysis, we wanted to do some sanity checks first of all. And the first thing we looked at is, do the constraints from the lensing PDF fit with our expectations for a Gaussian field, where we know that 2-point statistics will be optimal. So that's what we did. Here we have the constraints on omega m and sigma 8. And the red, grey, and blue contours here are all from this lensing PDF as you change the amount of smoothing, so you're changing the scales of the structures which you probe. And you see this really cool effect where the contours rotate and you have this degeneracy breaking. So when you combine those 3 things, you get this orange contour, which you almost can't see, but it's just here. It's a big improvement on constraining power. And we can compare that with the black contour, which is your standard 2-point statistic. This is the thing that is optimal for a Gaussian field. And sure enough, you see that the combined PDF constraint approaches the constraining power of the power spectrum, but does not exceed it because it's optimal. And we can also see that from this dashed pink line, which is the combination of all of these statistics. That corresponds exactly with the power spectrum, which shows the PDF does not contain any information that the power spectrum doesn't already contain, because this is a Gaussian field. So this was just a sanity check, all makes sense. Now let's move on to a field which is non-Gaussian. And we see a very different picture here, where the combination of the PDFs produces a very, very small orange contour which falls here, and it greatly outperforms the constraining power of the power spectrum. And that's because it's accessing that information that's beyond second order. Now, if we compare that with the dashed pink contour, which is you combine the power spectrum with that PDF, you see that, in fact, the dashed pink contour is exactly the same as the PDF combined. So the situation is reversed now. The power spectrum doesn't contribute any information to the analysis that the PDF doesn't already have. So now the PDF is the optimal statistic for this non-Gaussian field. So this was a first indication of how powerful this statistic could be. So we wanted to move on to more realistic cases and apply this to real data. In order to do that, I'm highlighting what we need to do to constrain cosmological parameters. We have to evaluate the likelihood, so the probability of data D given some cosmological parameters pi. And this depends on having a model for your cosmological, so a model for your lensing PDF as a function of cosmological parameters, and also preferably nuisance parameters. And also present is this covariance matrix, which we're going to measure all of this from numerical simulations, basically. So the simulations which we use are full n-body, dark matter only simulations called CosmoSlicks, and they vary in terms of all of these parameters here. Omega m, S8 here is a combination of omega m and sigma 8. So this is the statistic we commonly quote when we're quoting lensing constraints. It's a strength of clustering parameter. The Hubble parameter and W0. So each one of these little colored spots is an input cosmology for these simulations. So we measure the lensing PDFs from all of these different simulations, and then we train a machine learning algorithm called an emulator on the measurements from these simulations. And then effectively what we have is a numerical model which can make a prediction for the lensing PDF at arbitrary values of these parameters. So another way of saying that is the emulator interpolates between these points in this multi-dimensional space to give you a prediction wherever your MCMC sampler moves to. So here's a picture of the PDFs that we measure from the simulations. Y-axis is PDF, x-axis is the density in units of signal to noise. And we also measure this in many redshift bins. So we, up in this top corner, we have the measurement from low redshift, 0.1 to 0.3. Down here, it's high redshift, 0.9 to 1.2. And all of these off-diagonal panels, they are when you use the lensing information from pairs of redshift bins. So you can take the lensing information from redshift bin A and redshift bin B and use that collectively to reconstruct a density map from which you can measure a PDF, and that's what makes these things here. These are all color-coded by S8, so you get a flavor for the cosmological dependence of these things again. So these are the things that we train our emulator on. So we have a model, we can run an MCMC and get cosmological constraints. And that's what I'll show now. So these are constraints for simulated data with a true cosmology given by that blue crosshair. And the simulation is tailored to match the specifications of data from the kilo degree survey. So this is a current weak lensing survey. It's what we would call a stage 3 survey. And it's tailored to match in terms of the noise levels of that survey and the redshifts at which galaxies were observed in that survey. So in black, we have the constraint from the 2-point shear correlation function. In yellow is this PDF, which is actually the combination of PDFs measured with these different levels of smoothing. And in pink, we have the combination of the two things. And what we see is a 50% improvement on S8 and a 45% improvement on W0 compared to the standard approach, which is this correlation function. You'll notice that the correlation function is contributing information here. And you can see that from the fact this purple contour is smaller than the PDF. So there is information that the correlation function has in this analysis that the PDF doesn't. And the reason that is because this is quite noisy. This is a noisy regime. Stage 3 is quite a noise-dominated measurement. And the PDF is quite affected by noise in the data. So this is actually going to improve significantly if we perform this analysis again, but with data, with simulation tailored to match a stage 4 survey like LSST. We see this huge improvement when now the PDF is much more constraining than the correlation function. And when you look at the combination of the correlation function and PDF, you're not getting any extra information that the PDF didn't have already. And this is because it is a much higher signal-to-noise regime. And we see improvements in the precision on these parameters of about 85 to 98%, depending on the parameter that you consider. So this was all done in a systematics-free regime. What we want to now do is apply this to real data, and that means we have to worry about all these pesky systematics. One of the things is your irregular survey footprint. So this is what the survey footprint looks like for the kilo-degree survey. And this irregular footprint basically impacts your reconstruction of your projected density maps. So that means if this is in your data, but not in your model predictions, you're going to have a problem. It will be apples and oranges. So what we've spent the last year doing is repeating this analysis, but with this footprint built into the simulation. So it's now apples and apples. So that's taken care of. Another thing we've worked hard at looking at is intrinsic galaxy alignments. So this is a contaminant to the weak lensing signal. This is because galaxies are not uncorrelated before lensing. They have some intrinsic alignment, some intrinsic correlation. So what we did was use simulations to model the impact of this intrinsic alignment on the PDF. And all these different colored lines are as you toggle the strength of the intrinsic alignment of galaxies. And you can see it affects certain redshift bins much more than others. And we have some preliminary results that suggest that this doesn't bias the lensing PDF constraints so much, but we're still stress testing those, looking into the robustness, but we think we've got a good handle on the intrinsic alignment systematic and its effect on the statistic at the moment. Things on our to-do list are looking at the impact of baryonic feedback, so the impact of AGN and supernova changes matter distributions on small scales, and also whether you've really got your photometric redshifts for your galaxies estimated correctly, and what is the impact of that if you don't on this statistic. So to summarize, there's information beyond second order present in our data. We propose extracting it with this lensing PDF measured on different scales because that optimizes constraining power. For stage 3-like surveys, for example, kilo-degree survey, we found improvements on parameters of like 30 to 50%. But the future is very bright. With LSST, we predict this is going to improve a lot because of the improvements in signal to noise. And we're currently working on modeling systematics so as to apply this to data from kids. Please read this paper. That's it. Thank you.
Okay, questions?
Thank you for the talk. I was surprised to see how the intrinsic alignment was affecting only certain redshift bins, and I don't have a good intuition about what wavelength it's coming from. So could you perhaps illustrate this a bit?
Yeah, sure. So there are two types of intrinsic alignments. There's ones that affect galaxies at the same redshift, and then there's another intrinsic alignment that affects galaxies at very different redshifts, and that's because they're correlated with some large-scale tidal field. And it's that second intrinsic alignment which is known to be the larger of the two. That's the one that would affect the measurement in these bins, because these are looking at galaxies at very different redshifts.
Thank you.
Hi, thank you for the talk. I have questions about the LSST constraints. You use Gaussian processes for the, okay.
Yeah.
And what is the error on the predictions?
The error on the Gaussian process?
Yes, and do you propagate that error into the inference?
No, that's a very good point. And so it's not been propagated into the covariance here. That is something I think we would need to do when we're going to apply this to real data. Here, I don't think that is too big an issue because, for one thing, the data here is simulated, so it's exactly the same as the measurements which were used to train the emulator. And also, the correlation function constraints are also from the emulator, so that really what we were interested in here is what is the relative power of the PDF to the correlation function. So they're both impacted by, there's some error on your Gaussian process, but assuming it's about equal for both of them, it's okay not to include it. But we would need to do that for real data, certainly.
Yeah, but even for mock data, the errors on power spectrum might be different from PDF. Also depends on what smoothing scale you're using, right? So I'm just wondering, because I also have struggling with the LSSD emulator, so that's why I asked.
Yeah, if that assumption doesn't hold up, that one is emulated more accurately than the other, then this would affect this quantification, but I don't think we've got a prior reason to think one is easier or harder to emulate, I think.
And here your PDF is how many smoothing scales, or you just
3?
The 3. And power spectrum. So how long is your data vector?
So the PDF is measured in 15 redshift bins with 4 kappa bins per redshift bin and 3 scales. That makes 180 elements in the PDF measurement. The correlation function is larger, so it's 15 redshift bins times 9 theta bins times 2 components of the correlation function. It's 270, so it's...
And your variance is 900 or something simulation?
Yes.
Okay.
Yeah.
Okay. Thank you.
Hi there, thanks for your talk. So do you have an estimate as to how your constraints will change if you give up lambda CDM?
Well, we are varying W0 here, so so we are probing non-lambda CDM cosmologies as well. So we do get some quite powerful constraints on W0 forecasted. So and we think that's due to the fact that we are probing these very low density regions of the universe where dark energy should dominate.
But your lens in this lambda CDM line, right? You don't have any modification in the lens.
So the simulations that these measurements are measured from are not all lambda CDM cosmologies, because W0 is changing. So
yeah, but on the linear level, you assume lambda CDM, right?
I don't know if that's an assumption that goes into the production of the simulations, but I didn't work specifically on producing those. So I think, I'm not quite sure if that is an assumption that goes into them.
This is a very naive question. I was a bit confused when you were explaining pedagogically the different smoothing scales, right? So to me it looked like, obviously these things aren't you double counting here? Because it's the same information, you just resampling it 3 times. Isn't it, you see my worry here? Aren't you using the same data 3 times?
Yeah, so we know we know we're not double counting because we are modeling the covariance of all of these things and you know, including all that correlation between them in modeling that covariance. But I don't think it's all the same information because I think this is akin to measuring, you know, your power spectrum on different scales. Essentially, you know, this is a a large scale measurement, and this is a small scale measurement, I think.
Please let's take the speaker again.